We're about to start a 2-day section on optimization, which simply means finding the maximum and minimum values of a function. Now, a lot of people think, well, why would I need to know that? I'm not even going to go into a STEM field. I'm going to go into, say, econ. I'm like, oh, I think you should be very interested. I mean, you're going to run a business. Don't you want to maximize your profit, minimize cost, maximize employee production, minimize waste? You're going to be maxing and minning everything every day. And so if you can't do calculus, you can always hire a consultant to do it for you and pay them. Maybe that could be a good retirement gig for me. Who knows? All right, here are our steps for solving max-min optimization problems. Step 1, you want to make a picture of it. Whenever I panic on a test or quiz, that's always the first thing I do anyway, is I just start drawing or doodling. Once you have the picture drawn, you're going to write an equation. It's usually from geometry. Frequent flyers as far as equations go would be Pythagorean theorem. That's a good standby. SOHCAHTOA, your right triangle trig. Some of the harder problems, you might have to delve into a law of sines or a law of cosines or some formulas for 3D objects like the volume of a cylinder, kind of thing. But it's usually from geometry. Step 3, eliminate a variable, if possible. Sometimes it may not be possible, and that's totally fine. Finally, step 4, we take a derivative. That's what we do. That's the calculus step. And then we finish off by testing the critical points where the derivative is 0 or undefined. And we have to test the endpoints. A lot of students forget to test the endpoints, but we've seen already earlier in the chapter that absolute maxes and mins can occur at the ends. So we do need to take them into account. And finally, last but not least, make sure your answer isn't ridiculous. Just take a second look at it, make sure that it seems to make sense. All right, the best way to do it is to do it, so let's go. Example number 1, you've got this square sheet of metal. It's got an area of 121 square inches. Well, if that's a square, to me right away I know that the sides are 11 inches. This is 11 by 11. I'm going to go ahead and draw the picture and label the parts right now. Okay, you're going to make an open top box out of that. I don't know how visual you are. I don't know if you could do origami or if you can fold this in your mind, but if you cut those 4 white squares out of the corners and fold it up, you're going to end up with this 3-dimensional box with no top. Now, if you cut the squares really small, in fact, each of these squares, I'm going to call them X by X. Again, I'm drawing a picture, labeling the parts. If you fold this, wouldn't X be like the new height of this box? That's how high it is. So if you cut small squares, your box is not going to be very tall. But the base will be bigger. If you cut bigger squares, you're going to have a tall, slender box, but it's going to be more like a non-round test tube. It's going to be tall like a skyscraper, but not a whole lot of things on each floor. So the best thing to do is probably somewhere in the middle, and that's where calc comes in. All right, so this 3-dimensional box, we have to figure out how to label it. How long is each side? Remember, it came from a square, and it still will be a square. It started at 11 inches, but you cut off X from each end. So these will be a pair of 11 minus 2 X's. You want to make the box hold as much as possible. What's that really mean? It means you want to maximize the volume. And to maximize volume, you better start with a volume formula. What's the volume of the box, or any box? Well, length times width times height, which in this case would be X times 11 minus 2X squared. All right, let's see how we're doing so far. Let's go back to our rules of the game. Step 1, draw a picture, label the parts. We did that. Write an equation from geometry. We use length times width times height. Eliminate a variable. It wasn't even necessary. You only have one variable, that's X. So it's time for step 4, the blue step. We're going to take a derivative using some calc. And this problem, as it stands, is a product rule. Now, I don't have to do the product rule. I could square it out. I'm going to square it out. I think that'll be easier and quicker. I don't know about quicker. They're probably about the same. You know, take the squared off and just FOIL it. I'm going to end up with 121 minus 22x minus another 22x. So that's minus 44x. And then negative times negative, that's plus 4x squared. And then finally, we'll do some distributive properties. Crank all the powers up by 1. All right, that's the volume of the box. I still have not taken the derivative. I will do that here in blue. Volume prime, V prime, or dVdx, your teacher might call it. That's fine too. 121x, that becomes 121 minus 88x plus 12x squared. And we want to find the critical points, so we set that equal to 0. We can't make it undefined because there's no fractions. So we'll set it equal to 0. You're not going to believe this, but this thing actually does factor. Let me switch it around a little bit just so it's not quite so crazy looking. I'll put it in descending order. All right, that's going to factor into 2 parentheses. Only way to get 121 is 11 times 11. How about 2x and 6x, though? That's going to work if we make them both negative. As you can see, we got a negative 66x and another negative 22x. That's the negative 88. So that is going to work. So your critical numbers, x is either going to be, let's see, first parentheses, if I set that equal to 0, 11 halves. Or if you set the second parentheses equal to 0, x is going to be 11 sixths. Now remember that we take derivatives and set them equal to 0 to find the max and the min. So one of those is the smartest thing I could possibly do, and one is the dumbest. And as a CEO of one of the biggest corporations around, you don't want to do the dumbest thing possible as your main decision that you make every year. It's a good way to get yourself fired by the Board of Trustees. Which one do I keep? And the answer here is 11 sixths, or 1 5/6 inches. That's what I want to use. This will be the answer. Make sure I got my units on there. I'll spell it out. Right, so you want to cut off 1 5/6 inches squares from each corner of that rectangle. What's wrong with the 11 halves? Well, 11 halves is 5.5 as a decimal. Can you imagine cutting off 5.5 inches from each side? I can tell you what the volume would be when you folded that up. It'd be 0. Because you wouldn't have anything left to fold, because 5.5 plus another 5.5 is the entire 11. You would cut 4 big squares and they would all just fall off and you wouldn't have anything left. So 11 halves showed up because that's a minimum. That minimizes the volume of the box. The volume's 0. 11 sixths will maximize it. What's cool about this is we can graph it. And the poor pre-calc kids, pre-calc did a lot of problems like this. I know that when I taught honors pre-calculus, we would have this. But we would get to this point right here that I boxed up, and they didn't know what a derivative was, so they would just have to graph that thing and see where the max and mins were. So I'm going to do that right now. I'm going to graph that. Okay, here we go. Let's graph it. And as you can see, the min happens right here where my mouse is kind of hovering. That's 5.5. And the volume would be 0. We saw that because you would have cut the corners all the way off. In fact, we would have to change this window. A lot of times pre-calc kids struggle with this. You know, they do well on their homework and then they get on the test or quiz and they have to graph something and they're like, I can't find, it's off the page, and they get all panicked. X, okay, we know we have to cut something off, so we make the x min 0. The x max is 5.5 because you can't go that big. X scale, Y scale, I never change those. Y in this case is the volume. We're not going to have anything less than 0. Let's make the volume bigger. Instead of 10, let's make it 200. I might have to play around to make it bigger. Let's see. Oh, that was good. All right. There's the max. If you were in pre-calc, you would go second calc maximum, number 4. I could just type a 4. I'll cruise down there. Left bound. Yeah, that's safe. Enter. Right bound, just get past the hill there. Enter. You want me to guess? Yeah, sure. There it is, 1.833333. That's the max. That's 1 5/6. Now notice that the calculator does have a glitch. It shouldn't have a 2.6 at the end. It's 1.83333 forever. I'll teach this 2 or 3 times a day, and I'll get different answers each time I use the calculator. A little disconcerting, but that's a glitch that they're aware of. All the major calculator companies have little glitches still. Maybe by the time you guys have kids, they'll be fixed, but for now, they're there. All right, let's try something totally different. This time you're a landowner, and you've got a lot of land because you're able to purchase 42,000 feet of fencing from like Home Depot or Lowe's or Menards or somewhere like that, big box store. You have to have a lot of land and a lot of money to purchase that much fencing. And you're going to subdivide your property into 5 congruent rectangles as shown. You want to place this fencing so that the green area inside will be maximized. You want to maximize your land area. There aren't stupid things you can do with fencing. I mean, what if you took fencing and you went like 5 miles out and you made it like this wide and you came 5 miles back? I mean, your cattle wouldn't have any room to move. You know, even your household pets, they'd have to turn around carefully. That'd be dumb. In fact, in middle school, the best thing to do is to make a square. That would maximize the area. Unfortunately here, these will not be squares. And if you do make them squares, you could have done better. There's a better answer than that. And that's where calculus comes into play. So let's start by drawing a picture, labeling the parts. I like to call all the vertical pieces Y, and the horizontal pieces I like to call X. Now I could call the entire side X, or I can chop them up and call each little part X. I'm going to do that because I'd rather deal with a 5X than an X over 5. You know, the less number of fractions I have, the better my life is. So that's what we're going to do. Okay, so we have 10 X's plus, now it looks like 2Y, but there's got to be fencing in between the yards. We don't want the people's, cattle starting to get after the other people's cattle. We don't want any of that stuff. So really we're going to actually have 6Y. So 10X plus 6Y. And that'll be that 42,000 feet of fencing that you purchased. But we don't want to dig holes. If you've ever made a post hole, you know you don't want to do it more than once. You don't want to change your mind and be like, oh, that's the wrong place. That's not cool. So we want to maximize area. And the area of the entire green thing is 5XY. Or you could just say the area is XY. That's what I'm going to do. I'm not going to use the 5. It's optional. What will happen is if you use the 5, you'll end up setting it equal to 0, and when you divide both sides by 5, it won't matter. Since these are all congruent rectangles, my thinking is if I maximize the area of one, I'm going to maximize the area of them all simultaneously. So why bother with bigger numbers when I don't need them? So I'm going to take that xy, I'm going to maximize it, so I need to take its derivative, but I don't want to take the derivative yet because it's x times y, and I don't want to do a product rule, and then y is the wrong letter. I'm like, oops, wrong letter, and I'll have implicit differentiation. It's just going to be a big mess. And so instead, we use the fencing equation over there with the 42,000 as a substitution equation to knock out one of the variables. Again, let's see how we're doing so far. We'll go back to the step-by-step. Draw a picture, label the parts. That's done. Write an equation from geometry. I've written 2 of them. I used more or less a perimeter type equation for fencing, and then I used the area of rectangle, length times width. All right, eliminate a variable if possible. That's where we are right now. We're doing that before we take the derivative because that's the easy way to go. I'm going to get rid of the y, so let's move the 10x to the other side. I'll divide everything by 6. So y equals, let's see, negative 10/6. That's negative 5/3 x plus 42,000 divided by 6. That's 7,000. So that will be my substitution equation. I will plug that in over here. So instead of writing the y, I will take the y out with my eraser, and I'll replace it with that. Okay, let's make this a little easier to deal with by doing distributive property. Okay, we've eliminated one of the variables. Now it's time for the one and only calculus step. Taking the derivative, area prime. That's going to be negative 10/3 x plus 7,000. You'll go ahead and set that equal to 0 and solve. Okay, I brought it over here to the left just to give myself a little bit more room. I'm going to multiply both sides by the reciprocal, 3/10. That allows me to cancel out the 3's and the 10's. That just feels good. In fact, talking about canceling, let's cancel this 10 with one of these. We'll make it 700. 700 times 3. X is going to be 2,100. Now the y is not 2,100 feet. The y is going to be something else. We'll take the 2,100, we'll dump it into here, multiply it by negative 5/3, add 7,000, see what that makes. I'm running out of room. Let's create a little bit of space for myself. All right, you put the 2,100 in. Let's make it a fraction. You can cancel that right away with the 3. 700 times negative. That's negative 3,500 plus 7,000. That's going to be 3,500. So y be 3,500 feet. So no, these were not squares. Not even close, really. They're very much rectangular. And if you make those dimensions, you'll use all 42,000 feet of fencing that you bought, and you'll have the largest yards possible. The moment you deviate from that, it's no good. Strange, but true. In fact, I'm going to graph just to prove to you that 2,100 is what you want to make the x. Okay, I graphed the equation for area that we had once I did our distributive property, the negative 5/3 x squared plus 7,000x. Let's go and change the window around a little bit. Since I knew that the answer for x was 2,100, at least that's what I hope it is, I made x go from 0 to 4,000, figuring that 2,100 would be kind of middle-ish. X scale, again, I never change. Keep in mind that the y here is not the y on the graph. The y is the area. This equation is area equals, so I have to keep that in mind. And the area is going to be awful large. If these things are 2,100 by 3,500, that's huge. Let's make it, this ought to do it. There, that's better. All right, second calc, maximum, which is number 4. Left bound, enter. Right bound. Again, we're hoping to see our answer of 2,100 feet. And there it is, right down in the corner, 2,100. Again, there's a little bit of a glitch. And the greatest area that we can get is a cool 7.35 million square feet. Here, let me go ahead and put 2,100 in directly. There we go. The moment I move away from 2,100, I start to lose area. If I move away in either direction, you can see I start to lose the area. Coming over on that side, same thing. The y numbers, which is the area, starting to decrease. So yeah, 2,100 is the best thing to do. That forces the y to be 3,500. All right, one more, we'll take a break, and then we'll do the last 4 on day number 2. So here's number 3. We'll wrap this up. An open top box is to be constructed so that it will hold a volume of 2 cubic meters. The box is going to be 1 meter wide. That's the only thing that the corporation that I'm working for wants. Maybe their shelves are 1 meter wide, and they want the forklifts to be able to put this on the shelf properly. And They have high ceilings, so they don't care how high the box is or how wide they are. They want them to be 1 meter deep, or wide in this case. All right. The other thing is it costs $10 per square meter to make the base, but the sides, which are called lateral faces, are made out of the cheap stuff that are only half as expensive. We know that companies do that on purpose when they make, soda cans or pop cans. The tops and bottoms are really strong, reinforced, where the sides are aluminum that's so thin that you can crush it with your hands. And that's what we have here. Okay, so the top and bottom are going to cost $10 per square meter. The sides, lateral faces, will be $5 per square meter. Find the dimensions that will minimize your cost. And what is the minimum cost? After all, if you're in business, you want to minimize the cost of things. You want to be able to sell this box that holds 2 cubic meters, but you don't want to make the box expensive for yourself. So we need to label some parts. I'm going to call the front side here X because it's horizontal. I'll call this side Y since it's vertical, and this side over here is already 1. That's not going to change. So the volume is, again, length times width times height, which will be X times Y times 1, or XY. Oh, but wait, I know that the volume is supposed to be 2 cubic meters, so I can erase the volume and replace it with a 2. There we go. XY equals 2. That's one equation from geometry. I've got the picture drawn, parts labeled. I need another equation. And I'm not trying to minimize volume, so I won't be taking the derivative of the volume. I want to minimize the cost. And so I need a cost equation to take a derivative of. And the cost is based on the surface area, because that's what the box is made out of. The volume is more the liquid or solid inside. All right, so the cost, surface area of this box. Let's start with the expensive sides first at $10. I should say expensive side, because remember there's no top on this. So the bottom is simply going to be, if you look at this rectangle down here, 1 by X, that's just X. So far we have the cost is 10X, that's the bottom, plus 4 sides, and these are made of cheaper material, which is $5 per square meter. But the 4 sides are not all the same. You've got 2 pairs. The front and the back, if I take the front and just sort of highlight it here in red, that's X times Y. And so is the back, so that's going to be 2 XYs. The left and the right-hand side, if I go this way, the right is Y times 1, that's Y. The left is also Y, so that's plus 2Y. And that is your cost formula as soon as I give myself the right parentheses that I owe. There, that's better. All right, let's see how we're doing so far. Draw a picture, label the parts. That's been done. Equation from geometry. I made 2 of them. Okay, we have to eliminate a variable. Here we go. That's where we're at. And that's what this top equation, this 2 equals xy, can do. In fact, if xy is 2, really I'm looking at 2 times 2 in red here. That's a 4. And if I divide both sides of this equation by x, anytime I see y, I can replace a y with a 2 over x. So really, we're looking at 4 over x. All right, let me replace that. All right, good. We're down to 1 variable. We eliminated the y's. We're going to take a derivative. We'll set it equal to 0 and test the critical points and endpoints, and then just make sure our answer makes sense. All right, before I take a derivative, let me just clean it up a little bit, because it does look a little sloppy. The cost will be 10x plus 20 plus 20 over x, which is the same as 20x to the negative first, since I'm going to be doing some calc. I'd rather write it like that. And we take the derivative, so we're going to have cost prime. That'll simply be 10. Derivative of 20, of course, is 0, minus 20 x to the negative second. All right. I don't have to worry about the endpoint so much because the endpoint would be if x is 0, and that would squash the box flat. So the answer is going to come from this derivative. Let's set it equal to 0. I want to rewrite it since I have to do some algebra. So if I add 20 x to the negative second to both sides, I'm going to have 10 equals 20. But instead of saying x to the negative second, I'll write it down here as 20 over x squared. I'll make that a fraction also. If you cross multiply, you get 10x squared is 20, which means that x squared is 2. So x is the square root of 2. Now remember that we had xy equals 2 back in the day. If x is the square root of 2, y would also have to be the square root of 2, because that would make regular 2. So x is the square root of 2, y is also the square root of 2, and of course the third side has to be 1, and these are all in meters. So the dimensions that will minimize the cost are square root of 2 by square root of 2 by 1 meters. And then finally it says, what is the minimum cost? Well, we can just use the cost formula. I'll clear out some room. Let's see, 10 radical 2 plus 20 plus 20 over square root of 2. Well, 20 over square root of 2 is going to be another 10 rad 2. I think you'll be able to see it if we do this. Do a little bit of algebra 2. That becomes a regular 2. That cancels with the 20, and you're going to get 10 rad 2. So you have 10 rad 2 plus 10 rad 2. That's 20 rad 2 plus this $20 bill right here. The cheapest box you can make is $48.28. $48.28. All right, so that concludes day number 1 of optimization. 3 fairly different problems, and you can see the power of calculus. And it's not very difficult calculus. The difficult part, in my opinion, is the setup of it. And the calculus is simply just taking a derivative and plugging it back in. All right, we'll pick up with the last 4 problems, 4 through 7, on day number 2, coming up next. See you there.